Okay, let's dive right into this explainer and embark on what I promise will be a really eye-opening journey to uncover how forces truly interact in our universe. If you think you already have a solid handle on Newton's third law of motion, well, prepare to have a few of those foundational assumptions challenged today. We're going to look at the underlying physics governing literally everything from a simple walk down the street to the launch of a deep space rocket.
So to kick things off, I want you to picture this. A tiny firefly strikes a massive bus windshield as it's just barreling down the highway. Ask yourself, does the bus or the bug experience the greater force upon impact? It kind of feels like a trick question, right? I mean, common sense just screams that the massive bus must be hitting the bug with significantly more force.
But here is the totally counterintuitive answer. Neither experiences a greater force. The forces are exactly the same. No way, right? But it's true. The firefly only splatters because its tiny, fragile mass simply cannot withstand the massive acceleration resulting from that shared interaction. The bus experiences the exact same amount of force, but because of its colossal mass, that force doesn't even register as a change in speed.
Let's move to Section 1, the rule of interaction.
So Sir Isaac Newton published this brilliant observation all the way back in 1687 in his Principia Mathematica. He established that forces literally never exist in isolation. Never. They always occur in interaction pairs, resulting from a mutual physical dialogue between two objects. When one body exerts a force on another, the first body experiences a force that is perfectly equal in magnitude, but in the exact opposite direction.
And this next point really brilliantly illustrates the sheer mind-bending scale of this law. Just as the Earth pulls you down with gravitational force, keeping you nicely tethered to your chair right now, you are simultaneously pulling the Earth up with the exact same magnitude of force. That's right, you are pulling the Earth. The planet just happens to have a bit more mass than you do, so, we don't exactly notice it moving toward you.
Moving right along to Section 2, busting common force misconceptions.
Okay, take a look at this classic physics problem, highlighted by flipping physics. We've got a book resting on a table. You have the downward force of gravity pulling the book down, and the upward normal force of the table pushing the book up. Now, because the book isn't moving, these forces are equal and opposite. But here is the critical catch. They are actually not a Newton's third law pair. Why? Because both of these forces act on the exact same object, the book.
The CK12 Foundation makes a crystal clear point about this. True action and reaction forces are never balanced forces that just cancel each other out, precisely because they act on different objects. Think of two skaters standing facing each other on the ice. If one pushes the other, they both glide backward in opposite directions, right? The forces act on different bodies, creating movement for both.
We also really need to correct what physicists call the causal misinterpretation. Using the terms action and reaction can make it sound like one force causes the other in this sort of delayed, step-by-step chain of events. But in reality, action and reaction forces are perfectly simultaneous. It is an instant, mutual interaction, not a delayed cause and effect relationship.
Let's look at Section 3, animal and vehicle motion.
The really cool thing is that whether you're looking at a fish using its fins to push water backwards, a bird's wings pushing air downwards to create lift, or your car's tires gripping the road and pushing it backwards, the underlying principle is exactly identical. The animal or vehicle doesn't propel itself directly. Instead, it applies a force to its environment, and it's always the equal and opposite reaction force from the environment, the water, the air, the road, that actually generates that forward momentum.
Okay, on to Section 4, biomechanics in sports. Let's see how athletes master this.
In sports science, there's a specific term for this dynamic, ground reaction force, or GRF. It is literally the track, the court, or the turf aggressively pushing back against the athlete's body right after the athlete applies force down into it. The IB Sports Exercise and Health Science syllabus breaks this down into a really neat sequence. If a sprinter wants to surge forward out of the blocks, they can't just push straight down. That won't work. They must intentionally drive their foot down and backward into the track. As a simultaneous result, the track exerts a ground reaction force that pushes them up and forward, creating that massive explosive acceleration.
But remember, this law goes both ways. When that same athlete lands a jump, they hit the ground with significant force, and the ground hits them right back just as hard. So to survive this without blowing out a knee, athletes use specific joint flexion. They bend their knees and hips.
This technique buys them time, spreading that incoming ground reaction force over a longer period, which effectively reduces the peak force that travels up through their connective tissues. It's a real game changer for injury prevention.
Finally, Section 5. Rockets and relativistic limits. Let's scale things way, way up.
So here is a very common myth. Rockets need the Earth's atmosphere like they need air to push against in order to fly. But if that were true, how on earth would they steer in the total vacuum of deep space? In reality, rockets don't push against the air at all. They accelerate by burning fuel and aggressively pushing hot exhaust gases backward out of their engines. The exhaust acts as object A, the rocket as object B. By pushing the exhaust one way, the exhaust pushes the rocket the other way.
Take NASA's Space Launch System, which is built for the Artemis deep space missions. It relies entirely on this exact action-reaction principle. Through massive combustion, it forcefully expels gas to generate approximately 2,000 pounds of intense thrust right at liftoff, purely by exploiting Newton's third law.
However, classical physics isn't totally perfect, and we do have to acknowledge where the 17th century law finally meets its match. Newton's third law actually breaks down under some pretty extreme conditions. If objects are moving near the speed of light, relativistic differences emerge that require Einstein's formulas. If we zoom way into the atomic scale, quantum mechanics takes over. And in complex electromagnetism, the electromagnetic fields themselves can actually carry their own momentum. This means the forces between two charged particles might not seem perfectly balanced unless you account for the momentum held within that invisible field itself.
Yet, despite those extreme limitations, this research paper from the Journal of Pure and Applied Physics reminds us of a vital truth. As long as you aren't dealing with quantum atoms or light-speed travel, Newton's interaction pairs remain the absolute, undisputed foundation for modern engineering, global transportation, and human spaceflight. We literally build our entire modern world on this law.
So, as you go about your day-to-day, realizing that every single step you take is a perfectly matched physical dialogue with the Earth beneath your feet, I want to leave you with this final thought. As the Earth and the Sun perform their constant gravitational dance, pulling on each other with equal force across the vast void of space, what other invisible interactions are secretly shaping your every move right now? Thanks so much for joining me on this explainer, and keep questioning the forces around you.